So our next speaker is going to be Ian Mann.
Okay, thanks, Alexa. So for those who don't know me, I'm Ian Mann from the University of Alberta in Canada, and I'm going to present to you a brief overview of a Canadian radiation detector called SWEPT. It's the Sweeping Energetic Particle Telescope. And ostensibly, this provides a steerable radiation telescope for the energy and directional analysis of radiation that might be coming into the lunar environment. And this is work led out of the University of Alberta with our industrial partners at Honeywell and academic partners at the University of Calgary and also at the University of Iowa. So the development of this Canadian radiation instrument, I'll describe briefly the heritage in a moment, but it follows the kind of philosophy in the space exploration roadmap, the global space exploration roadmap. And as far as the radiation detection is concerned, we're envisaging the development of modular technology that takes us from space station in low Earth orbit, outside the protective magnetic shield of the Earth's magnetosphere, out to the moon. And of course, the revisit to moon with the Artemis program and related activities, including the Lunar Gateway, and then hopefully on to further exploration to perhaps the Red Planet and other destinations in the solar system. And our goal is ostensibly to have the capacity to measure energetic particles, but our focus is on solar energetic particles and look at the energy and directional spectrum of that. And I'll return to the importance of the directionality capability of this instrument later in the presentation. So a little bit of heritage. So this instrument's been in development at the University of Alberta since about 2005 for an orbital mission around the Earth called Orbitals. We looked at some concepts to fly on the station, and then actually with the focus on returning to the moon, Canadian Space Agency have supported a number of contracts very recently, looking at scientific opportunities and honing the design of this instrument for applications either in lunar orbit or also actually on the lunar surface as part of a lander. Most recently, we have funding for a new microsat mission in Earth orbit called Radicals, which will fall a version of this instrument. But for the purposes of this talk, I'm focusing on a current Canadian Space Agency contract that we have to build and test a prototype of this instrument with application for the Lunar Gateway. And the goal essentially of the instrument development is to prove the technology and to take the prototype instrument and validate its performance, including in accelerator beamlines, for example, at Triumph in Vancouver. And you can see in this schematic, the philosophy of this instrument is to actively steer the instrument to give us a measurement of the directionality of the radiation and how it evolves through the course of an SEP event. And that's very important because how that radiation is processed then will impact anything in the vicinity, electronics, and of course, most importantly, any astronauts inside the gateway or indeed on the lunar surface. And the processing of that radiation, especially the SEP protons, is important because the secondary production, for example, neutrons inside the gateway will be of significant biological impact for astronauts that are in board at the time. Now, of course, a piece of history, probably everybody knows here the risks are much larger outside the magnetic shield, and the Apollo program was rather fortunate in avoiding large solar energetic particle events on the lunar surface. But of course, as we return to the moon, we can't rely on being quite so lucky, and we need to have the capability to characterize the radiation and also to design mitigation strategies where information about incoming radiation storms and SEP storms would be available for the astronauts to take protective action, maybe to enter a shielded space or other mitigation strategies. And looking forward to the challenges, of course, the number of these SEP events peaks at solar max, and so there's an unfortunate, perhaps, coincidence between the start of the Artemis program and the time of the next solar maximum. Typically, SEP events occur around every couple of weeks at solar maximum, but they vary in size from relatively small, short-lasting events to more sporadic and intense events where the flux is orders of magnitude larger than the more continuous background galactic cosmic ray flux. And there's some interesting aspects around the directionality that's not well studied. This slide shows an example of a small SEP and a large SEP as a function of angle of arrival of that radiation. So often the events start, if they're magnetically connected to the sun, are strongly beamed along the direction of the IMF, and then they isotropize as a result of interactions with shocks or other structures in the heliosphere, or perhaps to the generation mechanism itself. But the isotropization time is quite different, can be short or long depending on the intensity of the event. And so the radiation environment that's experienced by astronauts, any infrastructure, and even on the surface of the moon, is going to be influenced by how that directionality evolves and anything that's in the way. And we think this is an important aspect for radiation protection, as well as, in fact, for studying the physical processes which accelerate the SEPs in the first place. So our goal, as I mentioned, is to have a sweeping technology to mount a directional telescopic instrument on a two-dimensional gimbal that will have access to all directions in 4 pi steradians of space, and to use that to sweep and characterize the radiation, both in a slow sweep during ambient conditions, and then to trigger and to accelerate that sweep more rapidly once an SEP event begins. Now I'm focusing here mostly on the protons, but we also have the capacity with this instrument to also measure electrons. And these lower mass electrons are believed to be a potential precursor, a warning, in fact, of the imminent arrival of subsequent SEP protons and alphas a little bit later. So maybe I'll skip through this slide in the interest of time. The message on the slide is that the NASA 30-day astronaut exposure limits can be reached fairly easily, depending on the amount of shielding that's used. So certainly these SEP events are a concern in terms of the astronaut dose that we need to pay attention to. So here's kind of the meat of the information. The basic design of the SWEPT, it's a telescopic detector, set of stacked silicon wafers. We anticipate sourcing these from Micron. We've built a prototype of this instrument previously and taken it to Triumph. And ostensibly the design has calorimetric measurement of the electrons in 2 detectors close to the entrance collimator, and then more elements in the stack deeper in the telescope that will provide measurements of the higher energy protons as they penetrate deeply into the stack. We use coincidence logic, back shielding, style shielding, and so on to create a high fidelity measurement of the protons and the alphas in the energy range of about 20 to 300 MeV for the protons, and higher than that for the alphas, going from around 100 MeV to over 1,000 MeV. And then the same telescope provides measurements for electrons in the range of about 400 keV up to maybe 5 MeV, with a goal of actually reducing the lower energy range of that. And that energy range is perfectly aligned with the energy range that's required for the putative electron warning signals that may precede an SEP event.
About 30 seconds or so left. Sorry, my internet
Sure.
cut out.
No, that's all right. So basically, the goal then here is to study space radiation environment on the gateway, including this angular element. It's complementary to the Ursa and Hermes packages that were already described. And significantly, the steerable capability also allows us to avoid perhaps some of the protrusions and obstructions that might impede measurements, for example, on merit as part of the Hermes payload. Clear applications to space health, and as I've mentioned, to test some of these algorithms, for example, those that Eric Posner has been suggesting, where we might use an electron channel in advance of that. I guess finally, I just mentioned the complementarity of other measurements and scattering from the regolith. So understanding the backscatter of particles from the regolith might give us a mechanism to understand some of the characteristics, perhaps even the water distribution that exists within the lunar regolith. Based on these crater observations, it suggests that might be something of value. And you could combine these measurements in orbit with others on the surface, or to use the periapsis passes to start to look at some of these characteristics, at least over the pole. So I'll leave my summary slide here, and thank you for your attention.
Thank you, Ian. This is great. Really great talk. I do see a question from Andre in the chat. Because I think we have maybe just time for one here quick. How does your instrument differentiate electrons and ions?
Right. So the simply put, the instrument uses a logic profile for the energy deposition in the stack of the different silicon wafers. So it's a DDX detector, somewhat like SST on Themis, which you'll be familiar with, Andre. But most of the electron detection is coming from the energy deposition in the first two wafers. So it's principally a calorimetric measurement. But the amount of energy that's differentially deposited in the different detectors allows you to construct energy channels that then give you, I mean, delta E over E is about 25 or 30% in the channel, something like that. And you can then differentiate on the basis of ostensibly a lookup table, the different species that you're seeing based on how they deposit their energy in the stack. So I hope that answers Andre's question.
Thank you.